Hello, I'm the chemistry guy. In this video, we will learn about the structure of the atom, and in particular about atomic orbitals.
Okay, let's get started. In the first lecture, we talked about the fact that everything was made up of atoms. An atom contains a heavy nucleus that is composed of positively charged protons and neutral neutrons, and then around this nucleus are negative electrons. In this presentation, we will expand on the structure of an atom, talk about atomic orbitals, and in the next lecture we will use this to explain the periodic table. We will start with the simplest element, the hydrogen atom, where we have a single proton in the nucleus about which a single electron travels. To a first approximation, we could assume that the electron orbits the proton like the moon orbits the Earth. Unfortunately, this doesn't work. If we view the orbiting electron edge on, it looks like the electron moves up and down as it goes around and around. This motion sends out electromagnetic radiation, and this is how a radio tower works. The electron will lose energy, and very quickly the negative electron will crash into the positive proton, and the atom will no longer exist. It was observed many years ago that even though the electron is a particle, it is so small and moves so quickly that it also displays the property of a wave. Waves are known to interfere with each other and reinforce one another, forming what is called a diffraction pattern, and the same thing was observed for the electron. Way back in the 1920s, scientists used quantum mechanics to solve for the energy of the electron, and the resulting equation produced a series of energy levels and corresponding wave functions. Since the electron has wave properties, you can only produce a probability distribution of where the electron might be on average. The form of this equation of wave function is given by this massive equation. Okay, I'm sure you all understand that completely. No, I'm kidding. Okay, don't be concerned with the equation. The only thing to note is that the wave function depends upon three quantum numbers, n, L, and M. Once we set these three quantum numbers, we can determine the wave function for the electron, which is just its probability distribution around the nucleus. Okay, n determines the size of this wave function. As n gets larger, the electron on average will be further from the nucleus. L determines the shape of this wave function, and M determines the orientation of the wave function. The quantum numbers have the following rules. N must be an integer 1, 2, 3 all the way up. For each value of n, L can be 0 all the way up to the number 1 less than n. And then for each value of L, M can be the integers from minus L all the way up to 0, all the way up to positive L. We will start at the beginning with n equals 1. Since L goes from 0 to the number 1 less than n, L can only be 0. Since M goes from minus L to L, M can only be 0. When L is equal to 0, the wave function is spherically shaped, which is why it cannot really have an orientation. This is called the 1s orbital. The 1 is the value of n, which is the principal quantum number, and the s is for spherical, or in this case L equals 0. Note that this is simply a plot shown here of the average electron density in the orbital. This means that about 99% of the time the electron will be inside this sphere and will not have any preference for being on one side or the other. For n equals 2, L can be 0 or 1. When L is equal to 0, M can only be 0, and we have a 2s orbital. This has the same electron density contour as the 1s, spherical in other words. It's just larger. When L is equal to 1, M can be minus 1, 0, and 1. These are called the 2p orbitals, and the density contours point along the x, z, and y axes respectively. You can kind of think of this as taking two balloons and holding the ends of the balloons together such that they push out in either direction. Okay? We call them the 2px, 2pz, and 2py orbitals. When n is equal to 3, L can be 0, 1, and 2. When L is 0, M is 0, and we have the 3s orbital. Again, this has a spherical electron density contour and is larger than the 2s orbital. When L is equal to 1, M can be minus 1, 0, and 1, and we have the 3p orbitals. Again, they look like the 2p orbitals, only they're larger. When L is equal to 2, M can be minus 2, minus 1, 0, 1, and 2. These are the 5 3d orbitals and are denoted dxy, dxz, dz squared, dyz, and dx squared minus y squared. As you can see, for most of them, they look like 4 balloons kind of held together but staying in a plane. When n is equal to 4, L can be 0, 1, 2, or 3. Again, when L is equal to 0, M is equal to 0, and we have a 4s orbital, which still has the spherical electron density, but it's much larger than the 3s orbital. For L is equal to 1, M can be minus 1, 0, or 1, and we have the 3 4p orbitals. For L is equal to 2, M is minus 2, minus 1, 0, 1, or 2, and we have the 5 4d orbitals. They look like the 3d orbitals in the last slide, just again larger. And for L is equal to 3, M can be minus 3, minus 2, minus 1, 0, 1, 2, or 3. These are called the 4f orbitals, and there are 7 of them. As you can see from the electron density contours, these f orbitals are quite unique. Okay, they've got many lobes. Sometimes they sit in the same, basically in the same plane. Sometimes they go across multiple planes. So to review, n is called the principal quantum number, and it determines the size of the electron density contour, which we can just call an orbital. If L determines the shape of the orbital, and they have a one-letter designation. For L is equal to 0, it's an s orbital. For L is equal to 1, it's a p orbital. For L equals 2, it's a d orbital. And for L equals 3, it's an f orbital. M determines the orientation of the electron density contour, and in general, there are 2L plus 1 such orbitals for each value of s. So when L is equal to 0, there's only one orientation for the s orbital. When L is equal to 1, there are 3 different orientations for the p orbital, and we would call them down the x, z, and y axes. When L is equal to 2, there are 5, and when L is equal to 3, there are 7 different f orbitals. One final point is that an electron behaves like a tiny magnet with a north and a south pole. This was observed when in atoms placed in a magnetic field where there was a slight difference in energy if the electron's magnetic field was pointed with or against the external magnetic field. We know that if a charged particle spins, it creates a magnetic field, so we call this the electron spin, and it is denoted by the quantum number s. S can have values of 1/2 and -1/2, which we just call spin up and spin down. Therefore, each electron in an atom is labeled by 4 quantum numbers, n, l, m, and s. The Pauli Exclusion Principle states that no 2 electrons in an atom can have the same 4 quantum numbers. This means that a specific orbital, which for atoms is a set of allowed values of the n, l, and m quantum numbers, can only hold at most 2 electrons, one spin up and one spin down. If an atom only has a single electron, the energy of the electron is only determined by the value of n. This means that the 2s and 3 2p orbitals all have the same energy. As soon as a second electron is added, this is no longer true. In the next video, we will use the periodic table to see how the orbital energies are affected as more electrons are present in the atom.
I hope you enjoyed this video, and if you enjoyed it, I hope you will support my Patreon page.